So hello, welcome to second day review for the exam. For those of you watching in the video, I said I would go over questions from whoever showed up today or any questions emailed me. No one emailed me any questions and only one of you's in the room right now. So I guess he gets a free review session that I'm recording for the rest of you. Let's see. Chapter 24. Is this just in general chapter 24? The question was, can I do chapter 24? Chapter 24 was all about induced EMFs. And questions from that chapter were mostly about the idea of if you have a changing magnetic flux, you will induce an EMF, where the EMF induced is negative N change in magnetic flux over change in time, where magnetic flux is BA cosine of the angle between B and of direction normal to the area. Sorry, opening up more problems as I talk. In general, the setup here was this idea of we had things with changing magnetic fields, like the magneto problem I did Monday. Things with changing magnetic fields, or maybe changing area, or maybe just them moving relative to each other, and how that can induce a magnetic field. So, why are you doing this to me, computer? Sorry, I have to put this over here for a second to see if, why can't I scroll to the side? It's being a real pain in the ass. So I could just do a problem on that if you want. I guess that would be the easiest way. Unless you ask for anything in particular. So, all right, I want to take a random problem from an old textbook. And the one I found, no. This thing is being a real pain in the ass using the digital copy of the textbook, but the physical copy of the textbook is in my office. So, won't be very useful. Okay. Oh, no one's in the room. If no one's here, I'm not going to do shit. Okay, and resuming recording. So, the problem I have, which I'm going to see what form I can put this up. There we go. This is from an old textbook, or the textbook I once used to use. And I'm going to do this question 10 right here. And it says, the flexible loop in figure blah, blah, blah has a radius of 12 centimeters. And is a magnetic field of strength 0.15 Tesla. The loop is grasped at point A and point B and stretched into the area is nearly zero. See, what this means is that we're changing the area. We're bringing the area initial of pi r squared, or pi times 0.12 squared, and we're bringing that area to zero. What that means is that will be a change in flux, and if the flux is changing, we induce a magnetic field. And it says it does this in 2 seconds. What's the induced EMF? What you're going to do when you do induced EMF problems is, for the most part, you're just going to take this equation and plug into here. This means induced EMF is negative N change in BA cosine theta over change in T. I don't know why I put that symbol, not change in. That was a mistake. Now, this negative sign is Lenz's law. That negative sign just means direction. When doing this, when you got this asks for the magnitude, and I would probably ask for the direction if we did it, and I'll get to a second what direction it would be in. But if I do direct, that's just to incorporate direction. You never need to plug in. And here it says N is how many loops it is, but it's a single loop. So in this case, n is 1. Now, theta. Theta is the angle between the loop and the magnetic field. If you remember when I taught this in class, I had this setup thing. Or if I talk about the loop going, it's whether the loop is in line with the magnetic field or if it's at some angle relative to it. And for this guy, what we'll say is that if you look at the drawing, that B is directly in. It's right along the normal of this magnetic field. That B is pointing right into it. That means it's an angle of 0 degrees. An angle of 0 degrees, meaning the cosine of the angle is 1. Now, how you normally solve these is anything that isn't changing, pull it out of the delta. That means it's B delta A over delta T. Now, a lot of the problems we've done, I'm not on the screen. A lot of the problems we've done, that delta A has meant different things. When we had one with the moving magnetic field, the moving loop into the magnetic field, we used that area is, x times y and use some velocity equations. But here, legitimately, the area is changing. So it'll just be B area final minus area initial over T. Now I'm going to get a negative answer. I already dropped the negative sign, not to, because I said I didn't care about it because of, that's just magnitude. I just wanted the magnitude. And so really I'm just going to say, we'll just cancel out the negative sign again. But my EMF will be then B, the area final is 0, negative AI over T. Once again, saying really there should have been a negative sign here. I got rid of it because I wanted magnitude. If I put that negative sign back in, now I definitely have magnitude. B, A initial over T. Or 0.15 Tesla times pi times 0.12 meters squared over 2 seconds, which we can just do that math. I don't have the answer in front of me, but we can get it. Now, most of the time, I'd also ask for direction. Induced EMF will oppose any movement. Now, direction of EMF is kind of complicated, but we could say the direction of the current. See, here we're decreasing the magnetic flux because we're decreasing the area. If we're going to decrease the magnetic flux, this will try to induce a magnetic field to oppose that. What it means is if the magnetic field is into the page, it's going to induce a magnetic field out because it's into the page and getting smaller. At least the magnetic field isn't getting smaller, but the flux is getting smaller. And if the flux is getting smaller, we want to make it bigger again. And so if it's decreasing into the page, we want one going out of the page to go against it. And using the right-hand rule, that means that current would be counterclockwise when this gets stretched. As I said, other things I could do is I might have a changing magnetic field, like the magneto problem I did on Monday. I might also do something about things moving. We did a problem like that in class. Give me a second. Chapter 24. We did a problem in class like this one, where it's being pulled, the loop is being pulled into the magnetic field. I'm not going to bother doing this one again because this was in the chapter 24 example problems. If you want to watch me do this problem, just open that YouTube video. Seems like a waste to do it again. But that's the same idea that I just said delta A over delta T is the length, is the width times height, and then used velocity. Any questions on that? Did that help at all? Okay. That's the type of stuff from chapter 24 probably. What else can I cover? What else would be good for review? Tim, you got anything? Yeah, chapter. Okay, so you're commenting because people watching the video just see me staring at the screen and don't see the chat happening. There is a chat happening. Ta-da! Chapter 27 is probably the most straightforward. I have the equation, these things over here, but also it's just this bit there. They all kind of straightforward. Did you ask before for a chapter 25 problem? Do I want to do something there?
Yeah, was that inductors, AC stuff?
Chapter 25 is AC stuff.
Yeah,
And so
yeah,
for the
that's totally
most
fine.
part, what I normally deal with in there is the idea of impedance. And why? Sorry, I'm going to make this bigger for a second and see if I make it smaller again, if I can center it in a not stupid way. Nope, I can't. Okay,
Dr. Lawrence, quick
yeah.
question. So on the exam, for chapter 25 question, we could have we could have a full range of a question being something like multiple parts, like, oh, find the impedance, find the phase angle,
Yes.
something like that. Yeah, that's totally
And
fine.
that's probably the most likely is multiple parts, finding impedance, finding phase angle, and all that stuff. Other things I might mix in is RMS versus max, or whatchamacallit, resonant frequency, and maybe transformers. Transformers are less likely just because it would be hard to work a transformer in with the other stuff. But that would be the main bit.
What about like C is lambda frequency? Like, are we even going to touch that? Because I know we touched on it in previous chapters and on the last exam more.
Sorry, say that again.
Like in reflection and refraction. Are we really going to touch on like wavelength, frequency, that stuff?
Oh,
Like, yeah, that.
I'm not going to do much with wavelength and frequency. I might do stuff with N as C over V.
Yeah,
I could do something with C equals lambda F, but we're going to cover that a lot heavier in later chapters, including that whole energy is H times F, energy is Planck's constant times frequency.
yeah.
That's going to become really important later on. And so I'm going to cover that heavier then. Um, so that won't really make a big deal on this exam. Um, there we go. Yeah. So do you want me to do an ROC one or?
Yeah, that'd be good. If Tim wants to see something else other than that, then yeah.
Okay. So let me once again just pull.
I'm good right now, just a little extra practice.
Okay. I'm gonna do this. You know what? Do, do, my screen is getting super busy. What I was thinking was I would do this problem right here, kind of arbitrarily. I actually haven't even read the problem yet, but it seemed like a good one to do. So it has an inductor, a capacitor, and a resistor are connected in series. 50 hertz AC generator connected in series to these elements produces a maximum current of 250 milliamps. Require the maximum voltage. Okay. See, we can say Ohm's law, V equals IR, if we just have a resistor or a DC circuit. But in an AC circuit, we don't deal with resistance, or not entirely. We deal with impedance. And we'll say V equals IZ. Well, this could be true for V RMS equals I RMS Z, or V max equals I max Z. And so in this one, they gave, so over there, they gave I max, they asked for V max. And so that just means I need Z. Z, which is impedance, is given as the square root of R squared plus XL minus XC quantity squared. And so to get that, you need XL and XC. Well, XL and XC are the capacitive reactance and inductive reactance. Oh, not respectively. I did it backwards. XL is inductive reactance. XL is capacitive reactance. I said in the opposite order. And so to find them, we'll just say XL is 2 pi FL, which in the case of the problem I'm doing here will be 2.5 times, was it 50 hertz? I should probably just read, times L, which is 400 millihenries. Now, 400 millihenries is just 0.4 henries. So 0.8, I should just plug it into a calculator. There's a pi there. I would have done it in my head, except pi. Meanwhile, x, this is an L, doesn't look very good. Xc is 1 over 2 pi Fc. And so it'll be 1 over 2 pi times 50 hertz times whatever C was. Now C was 4.43 microfarads, so 4.43 times 10 to the negative 6 farads. And I'll just do that. 2 times pi, that's not a pi. 2 times pi times 50 times 4.43 e negative 6. 1 divided by that mess, 718.532 ohms. And now that I have both of those, I'll plug into my Z equation. And say Z is going to be all squared, which was 500 ohms, plus XL, 125.664 ohms, minus XC, 718.532 ohms, squared, square root of. That minus this, squared, plus 500 squared, square root of. And now that I have Z, I can go back to this guy and say V max equals I max Z and just multiply together. One of the things about these problems in general is they really are just plug and chug. If I want to get fancy and tricky, it's probably going to be something, say, is the current leading the voltage, or is the voltage leading the current? That's as tricky and fancy as I get. I didn't actually finish the problem. I just didn't multiply I to X question together. There was a part B. What's the phase angle? Phase angle is the inverse tangent of XL minus XC over all. I mean, it's, you kind of just plug in. I said the other things I can get tricky is maybe I do something with resonant frequency. But if I go resonant frequency, it's just this equation right here. If I ask for power, it's just that equation right there. None of these really use anything crazy. Do you want me to finish through this one, or is that okay with what I did?
That's fine.
Right. Like, I don't know anything else. I really hate that my zoom wheel or my scroll wheel is zooming instead of moving things around. It's driving me crazy. Let's go back to over here so I can find stuff. You get to see my random traveler over here. Yeah. What else? What else can I look at?
I mean, I know it's a little early, but I mean, really, chapters 24 and 25 were the ones that I was a little hazy on. 26 and 27 were fine for me. I don't know if Tim has any
He just left.
other. Oh, he left. Okay.
I mean, we can stop early if you want.
If you don't mind, maybe just do one more. Chapter 26.
Chapter 26.
One?
Okay. Chapters 26 is the whole reflection Snell's law, right? Yeah. The
Yeah,
thing with this chapter is where I can get tricky with it is literally the geometry. It isn't, these buttons are not what they should be. I really wish I had my textbook and didn't leave it at school. It doesn't get tricky with like doing calculations. Just figure out what angles are what, right? Like, let me put this back up. We had oh, if I do this, like we had this problem on the homework, these two plane mirrors, and like it was just reflection, but what made it tricky was figuring out what angle was which and how they related to each other. I try not to make too many weird tricks on the exam. I don't want to, I don't want to make it hard if I can't. Um, let me find a problem that we haven't done yet. You know what? I'll do one problem. I'm going to do this one right here. I think this problem was on the homework, right?
Yeah.
Okay, that'll work. I don't mind doing homework ones. So, it says the light beam in this figure strikes surface 2 at the critical angle. Determine the angle of incidence. Well, they give us the critical angle. But theta c is the inverse sine as written. If you look at my equation, it's the inverse sine of n2 over n1. But I want to think about what that n2 over n1 means, because this assumes n1 is the material you're leaving, n2 is the material you're going into. That's always what you assume with normally Snell's law. If I want to look at this, I have to decide what material I'm going to call n1, what material I'm going to call n2. Now this starts in the ale. So I would normally say the ale is n1 to correspond to theta 1. And this is n2 to correspond to what I'm going to call theta 2 eventually for my Snell's law. That means this equation, I'm not going to write it like that, because what I'm going to say is that in this case, theta c is the inverse sine of n1 over n2. Because if you look at my diagram, when this hits the critical angle, it's coming out of n2, and it should be going into n1. It's not going into n1 because critical angle. Make sense why I did that? Be careful with that.
Yeah.
Now, if I take the sine of both sides, that means the sine of the critical angle equals n1 over n2. I'm going to use that in a tiny bit, but for now, let's just hold on to that. Because keep in mind, we know critical angle, it's 42 degrees. Actually, no, I won't hold on to it yet. I'll just do it. So the sine 42 equals n1 over n2, which means the sine, the n1 divided by n2 is, I said 42? 0.6691. Okay, now here's where it gets tricky. If I want to solve theta 1, I can use Snell's law if I knew theta 2. So I'm going to try to get theta 2. And how I'm going to do that is I'm first going to solve for this angle, which I'm going to call alpha right here. Because this 42 degrees, this line is normal to the surface. And so I can say theta c, which was 42, plus what I just called alpha must be 90. And that means alpha is 90 minus theta c, or alpha is 90 minus 42, which is 48. Using that, and I found a way to do this with Crickle once, but I can't remember what I did, is I can figure out what this angle is, which I'm going to call beta. Because I have a triangle here. I can say, and let me switch colors for this, that I have a triangle going here, here, here. And for any triangle, the sum of the angles is 180. So I can say 180 is alpha plus beta plus 60, because that 60 is marked. And that means beta is 180 minus 60 minus alpha, or 180 minus 60 minus 48. Well, 180 minus 60 minus 48 is 72. Thing is, I don't actually care about beta. What I want is this theta 2 right here, but that's a right angle. I'll just say beta plus theta 2 equals 90, which means theta 2 is 90 minus beta, or 90 minus 72, also known as 18. Now, what I accomplished with all that is now I have theta 2. Since I have theta 2, I want to find theta 1. I can Snell's law. N1 sine theta 1 equals N2 sine theta 2. And if I want to find theta 1, I'll divide both sides by N1. And I didn't give any values of N, but let's look what my equation turned into. It turned into N2 divided by N1. Now up here, I said I knew N1 divided by N2, which means N2 over N1 is 1 over 0.6691. And therefore the sine of theta 1 equals 1 divided by 0.6691 times the sine of 18 degrees.
Can you scroll down?
Yep, I was just realizing that. And so I can just do that. Okay, the sine of 18. The sine of 18 is 0.309. We'll divide that by 0.6691. And then we'll take the inverse sine. And my angle ends up being 27.5 degrees. I didn't know N1, I didn't know N2, but I knew the ratio. This, as I said, this is a little more complicated of one because I had to do these jumps of logic. But if I just do something with flat out law of reflection or law of refraction, it's just too simple. There's not enough to grade. It's more likely I do something where you plug in various pieces. Just be prepared with the equations. Try to plug them together as needed.
All right, great.
Okay.
I don't have any more questions.
Okay.
And it's
Well,
already 3:30.
yeah. Theoretically, I would have gone to 350 today, but you're the only one asking me questions, and no one emailed me any. So if you're good, everyone's good. Yeah. Other people, if you want me to review stuff, let me know. Send me questions or come to class. Other than that, I'll stop there and I'll post this video. Have a good day.